Cool. Yeah, so my name's Willem, and as mentioned, I'm a solutions engineer at ChainSafe, which is basically like a fancy name for a researcher. And yeah, I'd like to present something that I learned the other day that I thought was just really cool, and I'd love to share with you all. So this is how to fast exit from an optimistic rollup. And so, yeah, I'll present a bit of background on optimistic rollups for anybody who that's a new thing for. I'll kind of present the main insight, which is like how we can potentially skip this window in certain circumstances, which is a problem that plagues optimistic rollups. And then I'd like to talk about some kind of applications we've got within ChainSafe for using this in our bridges. Okay, so a quick overview of optimistic rollups. Basically, a rollup is a state tree, which is very similar to the state tree that's already inside an Ethereum block. The main difference being that the state transition computation happens off-chain rather than on-chain. So in a rollup, we still have a tree, and the root of this tree is held within a block. So that's our like commitment to some state at some point in time. All of the transactions also kind of go on-chain, although in a slightly different way to enforce ordering. And then an off-chain actor called the sequencer is responsible for applying all these transactions to the state to calculate a new state. So in this case, we're changing the color of one of the leaf nodes from green to red, and that's our state transition. So all around, it's like actually quite a simple model, and like I guess because of that, it's kind of floated as like the near-term scaling solution for Ethereum. Near-term in the sense that like it's probably not the ultimate scaling solution, but it is one that we can basically do immediately with the kind of technology that we have. So that's really exciting. And there's a bunch of projects which are doing amazing work, in particular Optimism, to make these a reality for day-to-day Ethereum use. And so to summarize, state transition computation is done off-chain and the state is committed on-chain. But the kind of the obvious thing that you might see with this is how can we be sure that the state transition was done correctly if the computation was done off-chain? Yeah, good question. Well, the way this is solved in optimistic rollups in particular is by using something called a fraud proof. And so in this case, the sequencer doesn't just post the new state root online, on-chain, sorry. They also post it along with a bond. And the bond is posted in such a way that anybody can kind of challenge their commitment to the new state. And if a challenge is made, then the whole state transition is re-executed on-chain. So this is a really expensive operation that we want to avoid, obviously. And so it's only done in the case where somebody in the world suspects that some kind of fraud has taken place in the state transition. So if fraud is detected, then the sequencer gets slashed, the challenger gets a reward, and the kind of invalid state that was found to contain a fraudulent transaction is rolled back to the last kind of known valid state. Although this could potentially be challenged as well, and it could continue to roll back. And crucially, any other state transitions that build off this one that's been classed as fraudulent also get rolled back. So everything kind of goes back to our last known good state. And so doing this kind of challenge is an expensive operation because it basically involves, calculating the state transition on chain, and whoever is the challenger has to pay the gas for that. And so nobody's going to do it basically unless there's a really good reason to, like they can be basically certain that they'll get a reward, and the reward should cover their gas costs. And so this also raises kind of an interesting question, which is like, if the rollup can be rolled back at any time because there could be a fraud in its history, what does this mean for finality? And so in particular, this comes up when we're exiting from a rollup to the main chain. So we could be transacting in the rollup with some kind of assets. We might want to exit these from the rollup back to the main chain to then transfer it to a different layer 2 or something like that. And if the rollup could be rolled back at any time, if we transfer back to the main chain and then the rollup is rolled back, then this essentially means we've kind of done a double spend. And so the way that this is solved in most optimistic rollup implementations is by using something called a challenge window. So the challenge window says that after some period of time, we'll consider the rollup state to be final, even if it's fraudulent. And this needs to be really long, which is a huge hassle. So it needs to be long because we need to make sure that within this rollup window, there's time for a challenger to post a fraud proof. And there has to be near certainty that this fraud proof can be fit within a block. So you could imagine a case where maybe a rollup sequencer would be able to fill all the block space for the space of the window, thus preventing anybody from posting a fraud proof, thus allowing them to include fraudulent transactions. So the window needs to be long enough that kind of conducting one of these denial of service block space attacks is prohibitively expensive. And the number that most people come up with is between 1 to 2 weeks, which is insane. So for finality in a rollup from the perspective of the chain takes 1 to 2 weeks. And as you can imagine, for most people, this is pretty much not acceptable. So this is a huge problem for adoption for optimistic rollups. So let's talk a bit about the kind of entry and exit procedures and kind of where this problem comes up. So entry onto a rollup is actually really simple. If we have some actor, which we'll call Ashley, on the main chain, they could transfer Ether into a contract where it becomes locked. This would cause a special transaction to be included by the sequencer, which then on the rollup would trigger the minting of some wrapped Ether, which will then be transferred to Ashley's account on the rollup. So the rollup doesn't actually deal with Ether, it kind of deals with a wrapped version of Ether that can be redeemed 1-for-1. So this is pretty simple, and this can be done pretty much in a short time period. Rollup exit is basically the same thing in reverse, that our actor would transfer the wrapped Ether, which would then be burnt. But then they have to wait for 1 to 2 weeks for that action of them burning the Ether to kind of pass outside of that challenge window and become final. Once the main chain can be 100% sure that this burning of the Ether can never be undone, then they can unlock the Ether on the main chain. So we just had to wait 1 to 2 weeks just to transfer to a different rollup. So there is one kind of really key insight, and this was the kind of insight that made me go, yeah, that's cool, and I should present this at the meetup. And this insight is that like a valid state root can never be proven invalid. And the implication of this is that a valid state root can never be rolled back. And so the chain can't know if a state root's valid without actually executing the transitions on chain. But anybody off chain can validate the transitions themselves, convince themselves that any particular state root is valid, and therefore convince themselves that it can never be rolled back. So in summary, the chain can never know that something is actually final unless it's outside the challenge window, but anybody off chain can validate the rollup themselves because it's all public data, and then they can be sure that there can never be a rollback. So with this in mind, it's actually really simple to devise a fast exit. So in this case, we have this kind of additional actor, which we call LP, which is a liquidity provider. And they're a kind of off-chain actor as well as on-chain. So if Ashley transfers their wrapped Ether into a contract where it's burnt, this liquidity provider off-chain can verify the rollup themselves up to the point where this Ether was burnt. They can check that everything is valid, and then they can know that this can never be rolled back. By observing this, it allows them to dispatch funds to Ashley immediately without waiting. Then 2 weeks later, the rollup will reach finality. This will unlock some Ether, and then this Ether will go to the liquidity provider rather than to Ashley. So effectively, they've kind of like provided the Ether to Ashley, and then 2 weeks later, they'll get it themselves. And so they wouldn't do this for free, I imagine, and they would expect some kind of fee in return for this. But crucially, like over time, this liquidity pool isn't going to be drained. It will probably actually accumulate Ether because of the fees. So there can be actors that provide the service for quick rollup exits. Before we go on, yeah, so that's super cool. So it actually means that this problem that a lot of people kind of tout with optimistic rollups of this like difficult exit period is actually not that big an issue at all. It just requires these actors called liquidity providers to exist, and if it's kind of worthwhile to do so, if they can get sufficient fees, I imagine they will exist. Cool. And it turns out that we can actually use a really similar technique with one of our ChainSafe products, ChainBridge. So ChainBridge is what's called a trusted federation bridge, which is that there's a kind of group of relayers. These relayers watch actions which take place on a chain or potentially on an L2, such as a rollup. When they see a particular action, they come to consensus that they all saw the same thing and that it was valid, and then they submit a transaction on a target chain. And the federation is authorized to do certain things on that chain, for example, to mint wrap tokens. And doing so is like a kind of semi-trusted way to do a bridge, but it's also a really simple way. And what this actually allows us to do is to do near instant roll up to roll up or roll up to a different chain exits. So in this case, if our actor actually could make some call on a contract, the relayers observe this. The relayers would then verify the roll up themselves, ensure that it was all valid up to the point where that happened, and then they could then vote, come to a consensus, and do some multi-sig thing and cause some action to take place on potentially another chain or another roll-up. And this could really open up the world of roll-ups and L2s by allowing kind of instant interoperability between multiple universes. And yeah, the same thing again. If the roll-up's valid, the roll-up, they can skip waiting for finality. And this allows us to do any kind of cross-chain call. So not necessarily limited to value transfers or token transfers, like it would be in the case of like fast exits. But this allows us to do kind of any cross-chain call near instantly. Cool, and that's all I got. So yeah, thanks very much.